a WikiVidi documentaries production. Don't forget to like and subscribe. Enjoy. Voyager 1. Voyager 1 is a space probe launched by NASA on September 5, 1977. Part of the Voyager program to study the outer solar system, Voyager 1 launched 16 days after its twin, Voyager 2. Having operated for as of, the spacecraft still communicates with the Deep Space Network to receive routine commands and return data. At a distance of approximately 13 billion miles from the Sun as of January 2, 2018. It is the farthest spacecraft and man-made object from Earth. The probe's objectives included flybys of Jupiter, Saturn and Saturn's large moon, Titan. While the spacecraft's course could have been altered to include a Pluto encounter by foregoing the Titan flyby, exploration of the Moon, which was known to have a substantial atmosphere, took priority. It studied the weather, magnetic fields and rings of the two planets, and was the first probe to provide detailed images of their moons. After completing its primary mission with the Flyby of Saturn on November 12, 1980, Voyager 1 became the third of 5 artificial objects to achieve the escape velocity that will allow them to leave the solar system. On August 25, 2012, Voyager 1 became the first spacecraft to cross the Heliopause and enter the interstellar medium. In a further testament to the robustness of Voyager 1, the Voyager team completed a successful test of the spacecraft's trajectory correction maneuver, thrusters on November 28, 2017. The last time these backup thrusters were fired up was in November 1980, 37 years prior. Voyager project manager Suzanne Dodd anticipates that successful utilization of the TSM thrusters will extend the Voyager mission by an additional 2 to 3 years. Voyager 1's extended mission is expected to continue until around 2025, when its radioisotope thermoelectric generators will no longer supply enough electric power to operate its scientific instruments. History. In the 1960s, a grand tour to study the outer planets was proposed, which prompted NASA to begin work on a mission in the early 1970s. Information gathered by the Pioneer 10 spacecraft helped Voyager's engineers design Voyager to cope more effectively with the intense radiation environment around Jupiter. Initially, Voyager 1 was planned as Mariner 11 of the Mariner program. Due to budget cuts, the mission was scaled back to be a flyby of Jupiter and Saturn and renamed the Mariner Jupiter-Saturn probes. As the program progressed, the name was later changed to Voyager, since the probe designs began to differ greatly from previous Mariner missions. Spacecraft components. Voyager 1 was constructed by the Jet Propulsion Laboratory. It has 16 hydrazine thrusters, 3-axis stabilization gyroscopes, and referencing instruments to keep the probe's radio antenna pointed toward Earth. Collectively, these instruments are part of the attitude and articulation control subsystem, along with redundant units of most instruments and 8 backup thrusters. The spacecraft also included 11 scientific instruments to study celestial objects such as planets as it travels through space. Communication system. The radio communication system of Voyager 1 was designed to be used up to and beyond the limits of the solar system. The communication system includes a 3.7 meters diameter parabolic dish high-gain antenna to send and receive radio waves via the 3 Deep Space Network stations on the Earth. The craft normally transmits data to Earth over Deep Space Network Channel 18, using a frequency of either 2.3 GHz or 8.4 GHz, while signals from Earth to Voyager are broadcast at 2.1 GHz. When Voyager 1 is unable to communicate directly with the Earth, its digital tape recorder can record about 64 kilobytes of data for transmission. At another time, signals from Voyager 1 take over 19 hours to reach Earth. Power. Voyager 1 has 3 radioisotope thermoelectric generators mounted on a boom. Each MHWRTG contains 24 pressed plutonium-238 oxide spheres. The RTGs generated about 470 W of electric power at the time of launch, with the remainder being dissipated as waste heat. The power output of the RTGs declines over time, but the craft's RTGs will continue to support some of its operations until 2025. As of Voyager 1 has % of the plutonium-238 that it did at launch. By 2050, it will have 56.5% left. Computers. Unlike the other onboard instruments, the operation of the cameras for visible light is not autonomous, but rather it is controlled by an imagined parameter table contained in one of the onboard digital computers, the Flight Data Subsystem. Since the 1990s, space probes usually have completely autonomous cameras. The Computer Command Subsystem controls the cameras. The CCS contains fixed computer programs such as command decoding, fault detection and correction routines, antenna pointing routines, and spacecraft sequencing routines. This computer is an improved version of the one that was used in the 1970s Viking orbiters. The hardware in both customs-built CCS subsystems in the Voyagers is identical. There is only a minor software modification for one of them that has a scientific subsystem that the other lacks. The Attitude and Articulation Control subsystem controls the spacecraft orientation. It keeps the high-gain antenna pointing towards the Earth, controls attitude changes, and points the scan platform. The custom-built systems on both Voyagers are the same. Launch and trajectory. The Voyager 1 probe was launched on September 5, 1977, from Launch Complex 41 at the Cape Canaveral Air Force Station, aboard a Titan EE launch vehicle. The Voyager 2 probe had been launched 2 weeks earlier, on August 20, 1977. Despite being launched later, Voyager 1 reached both Jupiter and Saturn sooner, following a shorter trajectory. Flyby of Jupiter. Voyager 1 began photographing Jupiter in January 1979. Its closest approach to Jupiter was on March 5, 1979, at a distance of about 349,000 kilometers from the planet's center. Because of the greater photographic resolution allowed by a closer approach, most observations of the moons, rings, magnetic fields, and the radiation belt environment of the Jovian system were made during the 48-hour period that bracketed the closest approach. Voyager 1 finished photographing the Jovian system in April 1979. Discovery of active volcanic activity on the moon Io was probably the greatest surprise. It was the first time active volcanoes had been seen on another body in the solar system. It appears that activity on Io affects the entire Jovian system. Io appears to be the primary source of matter that pervades the Jovian magnetosphere, the region of space that surrounds the planet influenced by the planet's strong magnetic field. Sulfur, oxygen, and sodium apparently erupted by Io's volcanoes and sputtered off the surface by impact of high-energy particles, were detected at the outer edge of the magnetosphere of Jupiter. The two Voyager space probes made a number of important discoveries about Jupiter, its satellites, its radiation belts, and its never-before-seen planetary rings. Flyby of Saturn. The gravitational assist trajectories at Jupiter were successfully carried out by both Voyagers, and the two spacecraft went on to visit Saturn and its system of moons and rings. Voyager 1 encountered Saturn in November 1980, with the closest approach on November 12, 1980, when the space probe came within 124,000 kilometers of Saturn's cloud tops. The space probe's cameras detected complex structures in the rings of Saturn, and its remote sensing instruments study the atmospheres of Saturn and its giant moon Titan. Voyager 1 found that about 7% of the volume of Saturn's upper atmosphere is helium, while almost all the rest is hydrogen. Since Saturn's internal helium abundance was expected to be the same as Jupiter's and the Sun's, the lower abundance of helium in the upper atmosphere may imply that the heavier helium may be slowly sinking through Saturn's hydrogen. That might explain the excess heat that Saturn radiates over energy it receives from the Sun. Winds blow at high speeds in Saturn, near the equator. The Voyagers measured winds about 500 meters per second. The wind blows mostly in an easterly direction. The Voyagers found auroral ultraviolet emissions of hydrogen at mid-latitudes in the atmosphere, and auroras at polar latitudes. The high-level auroral activity may lead to the formation of complex hydrocarbon molecules that are carried toward the equator. The mid-latitude auroras, which occur only in sunlit regions, remain a puzzle, since bombardment by electrons and ions, known to cause auroras on Earth, occurs primarily at high latitudes. Both Voyagers measured the rotation of Saturn at 10 hours, 39 minutes, 24 seconds. Voyager 1's mission included a flyby of Titan, Saturn's largest moon, which had long been known to have an atmosphere. Images taken by Pioneer 11 in 1979 had indicated the atmosphere was substantial and complex, further increasing interest. The Titan flyby occurred as the spacecraft entered the system to avoid any possibility of damage closer to Saturn, compromising observations, and approached to within 4,000 miles, passing behind Titan as seen from Earth and the Sun. Voyager's measurement of the atmosphere's effect on sunlight, and Earth-based measurement of its effect on the probe's radio signal were used to determine the atmosphere's composition, density, and pressure. Titan's mass was also measured by observing its effect on the probe's trajectory. Thick haze prevented any visual observation of the surface, but the measurement of the atmosphere's composition, temperature, and pressure led to speculation that lakes of liquid hydrocarbons could exist on the surface. Because observations of Titan were considered vital, the trajectory chosen for Voyager 1 was designed around the optimum Titan flyby, which took it below the south pole of Saturn, and out of the plane of the ecliptic, ending its planetary science mission. Had Voyager 1 failed or been unable to observe Titan, Voyager 2's trajectory would have been altered to incorporate the Titan flyby, precluding any visit to Uranus and Neptune. The trajectory Voyager 1 was launched into would not have allowed it to continue onto Uranus and Neptune, but could have been altered to avoid a Titan flyby and travel from Saturn to Pluto, arriving in 1986. Exit from the heliosphere. On February 14, 1990, Voyager 1 took the first ever family portrait of the Solar System as seen from outside, which includes the image of planet Earth known as Pale Blue Dot. Soon afterward its cameras were deactivated to conserve power and computer resources for other equipment. The camera software has been removed from the spacecraft, so it would now be complex to get them working again. Earth-side software and computers for reading the images are also no longer available. On February 17, 1998, Voyager 1 reached a distance of 69 astronomical units from the Sun and overtook Pioneer 10 as the most distant spacecraft from Earth. Traveling at about 17 kilometers per second, it has the fastest heliocentric recession speed of any spacecraft. As Voyager 1 headed for interstellar space, its instruments continued to study the Solar System. Jet Propulsion Laboratory scientists used the plasma wave experiments aboard Voyager 1 and 2 to look for the Heliopause, the boundary at which the solar wind transitions into the interstellar medium. The probe was moving with a relative velocity to the Sun of about 17,030 meters per second. With the velocity the probe is currently maintaining, Voyager 1 is traveling about 325 million miles per year, or approximately half a light year per 10 millennia. Termination shock. Scientists at the Johns Hopkins University Applied Physics Laboratory think that Voyager 1 entered the termination shock in February 2003. This marks the point where the solar wind slows down to subsonic speeds. Some other scientists expressed doubt. Discussed in the journal Nature of November 6, 2003. The issue would not be resolved until other data became available. Since Voyager 1's solar wind detector ceased functioning in 1990. This failure meant that termination shock detection would have to be inferred from the data from the other instruments on board. In May 2005, a NASA press release said that the consensus was that Voyager 1 was then in the Heliosheath. In a scientific session at the American Geophysical Union meeting in New Orleans on the morning of May 25, 2005, Ed Stone presented evidence that the craft crossed the termination shock in late 2004. This event is estimated to have occurred on December 15, 2004, at a distance of 94 astronomical units from the Sun. Heliosheath. On March 31, 2006, amateur radio operators from Ansat in Germany tracked and received radio waves from Voyager 1 using the 20-meter dish at Borkum with a long integration technique. Retrieved data was checked and verified against data from the Deep Space Network station at Madrid, Spain. This seems to be the first such amateur tracking of Voyager 1. It was confirmed on December 13. 2010 that Voyager 1 had passed the reach of the radial outward flow of the solar wind, as measured by the low-energy charged particle device. It is suspected that solar wind at this distance turns sideways, because of interstellar wind pushing against the heliosphere. Since June 2010, detection of solar wind had been consistently at zero, providing conclusive evidence of the event. On this date, the spacecraft was approximately 116 astronomical units or 10.8 billion miles from the Sun. Voyager 1 was commanded to change its orientation to measure the sideways motion of the solar wind at that location in space on March 2011. A test roll done in February had confirmed the spacecraft's ability to maneuver and reorient itself. The course of the spacecraft was not changed. It rotated 70 degrees counterclockwise with respect to Earth to detect the solar wind. This was the first time the spacecraft had done any major maneuvering since the family portrait photograph of the planets was taken in 1990. After the first roll, the spacecraft had no problem in reorienting itself with Alpha Centauri, Voyager 1's guide star, and it resumed sending transmissions back to Earth. Voyager 1 was expected to enter interstellar space at any time. Voyager 2 was still detecting outward flow of solar wind at that point, but it was estimated that in the following months or years it would experience the same conditions as Voyager 1. The spacecraft was reported at 12.44 degrees declination and 17.163 hours right ascension, and at an ecliptic latitude of 34.9 degrees, placing it in the constellation Ophiuchus as observed from the Earth on May 21, 2011. On December 1, 2011, it was announced that Voyager 1 had detected the first Lyman alpha radiation originating from the Milky Way galaxy. Lyman alpha radiation had previously been detected from other galaxies, but, because of interference from the Sun, the radiation from the Milky Way was not detectable. NASA announced on December 5, 2011, that Voyager 1 had entered a new region referred to as a cosmic purgatory. Within this stagnation region, charged particles streaming from the Sun slow and turn inward, and the solar system's magnetic field is doubled in strength as interstellar space appears to be applying pressure. Energetic particles originating in the solar system decline by nearly half, while the detection of high-energy electrons from outside increases 100-fold. The inner edge of the stagnation region is located approximately 113 astronomical units from the Sun. Heliopause. NASA announced in June 2012 that the probe was detecting changes in the environment that were suspected to correlate with arrival at the heliopause. Voyager 1 had reported a marked increase in its detection of charged particles from interstellar space, which are normally deflected by the solar winds within the heliosphere from the Sun. The craft thus began to enter the interstellar medium at the edge of the solar system. Voyager 1 became the first spacecraft to cross the heliopause in August 2012, then at a distance of 121 astronomical units from the Sun, although this was not confirmed for another year. As of September 2012, sunlight took 16.89 hours to get to Voyager 1, which was at a distance of 121 astronomical units. The apparent magnitude of the Sun from the spacecraft was -16.3. The spacecraft was traveling at relative to the Sun. It would need about 17,565 years at this speed to travel a light year. To compare, Proxima Centauri, the closest star to the Sun, is about 4.2 light-years distant. Were the spacecraft traveling in the direction of that star, 73,775 years would pass before Voyager 1 reaches it. In late 2012, researchers reported that particle data from the spacecraft suggested that the probe had passed through the heliopause. Measurements from the spacecraft revealed a steady rise since May in collisions with high-energy particles, which are thought to be cosmic rays emanating from supernova explosions far beyond the solar system, with a sharp increase in these collisions in late August. At the same time, in late August, there was a dramatic drop in collisions with low-energy particles, which are thought to originate from the Sun. Ed Ruloff, space scientist at Johns Hopkins University and principal investigator for the Low-Energy Charged Particle Instrument on the spacecraft, declared that most scientists involved with Voyager 1 would agree that these two criteria have been sufficiently satisfied. However, the last criterion for officially declaring that Voyager 1 had crossed the boundary, the expected change in magnetic field direction, had not been observed, which suggested to some that the nature of the edge of the heliosphere had been misjudged. On December 3, 2012, Voyager project scientist Ed Stone of the California Institute of Technology said, "Voyager has discovered a new region of the heliosphere that we had not realized was there. We're still inside, apparently, but the magnetic field now is connected to the outside. So it's like a highway letting particles in and out." The magnetic field in this region was 10 times more intense than Voyager 1 encountered before the termination shock. It was expected to be the last barrier before the spacecraft exited the solar system completely and entered interstellar space. In March 2013, it was announced that Voyager 1 might have become the first spacecraft to enter interstellar space, having detected a marked change in the plasma environment on August 25, 2012. However, until September 12, 2013, it was still an open question as to whether the new region was interstellar space or an unknown region of the solar system. At that time, the former alternative was officially confirmed. In 2013, Voyager 1 was exiting the solar system at a speed of about 3.6 astronomical units per year, while Voyager 2 is going slower, leaving the solar system at 3.3 astronomical units per year. Each year Voyager 1 increases its lead over Voyager 2. Voyager 1 reached a distance of 135 astronomical units from the Sun on May 18, 2016. By September 5, 2017 that had increased to about 139.64 astronomical units from the Sun, or just over 19 light hours, and at that time Voyager 2 was 115.32 astronomical units from the Sun. Its progress can be monitored at NASA's website. Brought to you by WikiVidi Documentaries. Would you like